Hello and welcome to mathematics class, and now we are going to learn about circles. So let us see what are the topics to be covered here. We will learn about circles and its related terms, which is just a review of what we had learnt in earlier classes. Then we will go to angles subtended by a chord at a point. Then perpendicular from the center to a chord. Circle through 3 points. Equal chords and their distances from the center. Angle subtended by an arc of a circle. And finally, cyclic quadrilaterals. So let us start off with the first topic, a quick review of the concepts which we had learnt in our earlier classes. Now, what is a circle actually? And we all know that it is a collection of all the points in a plane which are at a fixed distance from a fixed point in the plane, right? This is the fixed point, and if we maintain a fixed distance between that point and the second point by joining a line and just move it, we will get a circle, right? So let us see the various parts of a circle, or the terms which are related to a circle. So we all know what is a center lies, right? So we also know that the center lies at the center of a circle. Okay, so what is a radius? It is just the distance of the center from the periphery of the circle, distance of the center from any point on the circle, right? This red line shows a radius. Now what is a diameter? Diameter is a straight line which joins 2 points on a circle and is passing through the center, right? And diameter is nothing but twice of radius, right? This part is a radius and this part is also a radius. Okay, so what are sectors? The parts enclosed by 2 radii, this radius and a part of the circle. This entire part is called one sector. This part is also called a sector, and this whole part is also called a sector, right? So you can see only a part of a circle and 2 radii, right? These 3 parts enclose a sector. Now what is a chord? A chord is just a straight line joining 2 points of a circle. It need not pass through the center. Chord only joins 2 points of a circle, and actually if you see, diameter is the longest chord, right? Diameter is the longest chord which also passes through the center, right? Chord need not pass through the center. Chords need not pass through the center, but diameter is one of the chords which passes through the center, and it is the longest chord among all the chords of a circle. And here we can see a segment. A segment is nothing but the region enclosed by a chord and one part of the circle, right? One part of the periphery of the circle. So this entire region is called a segment, and the parts of the circles which I was talking about, those are called as arcs. The part of the periphery of the circle, this is one arc, the orange part which is shown here. This is one of the arcs. This is another arc which is the part of a circle. This is one more arc which is the part of a circle, right? Any part of the periphery of the circle can be called as an arc. And of course there are major arcs, minor arcs, major sectors and minor sectors. And what are those? From the name only you can understand. Major are those which are the biggest or bigger than all the others, and minors are the smaller ones. Like here we have the biggest arc shown in this picture, which is the major arc, and the smallest one is the minor arc. And here the biggest sector, we have major sector, and the smallest one the minor sector. And similarly we can find out which is the major segment and the minor segment. This is the minor segment, right? And this entire part which is above the chord is the major segment, right? So now you know what are the parts of a circle and what are the major and minor parts according to their definitions. So let's move on to the next topic, angle subtended by a chord at a point. And now what does it mean? You can see if we have three chords AB, CD and EF, and the angle subtended by these chords at the center, or we join the two endpoints of the chord to the center, the angle which is made by them is the angle subtended by them at the center, right? The angles which they make when their endpoints are joined to the center, this is called angle subtended by the corresponding chords at the center of the circle, right? So there are many characteristics and very interesting ones which we can find out from these angles subtended by these chords. So here is one of them. It is stated as a theorem, which is equal chords of a circle subtend equal angles at the center. Or if we consider AB and CD as equal chords, right, there can be many different varieties of chords of a circle. The smallest one will be nearer to one of the sides of it, or one of the periphery part of the circle, right? The smallest chord will be nearer to the periphery of the circle, and the biggest chord is actually the diameter. So we have a large variation of chords, and if we pick out two of them which are equal, and here which we have named as AB and CD, if they are equal, they subtend equal angles at the center, or these two angles must be equal. So let us see how is this possible. Let us consider these two triangles AOB and triangle COD. Let us consider these two triangles. So we can see OA equals OC, right? Because the length is just the radius of the circle. Then OB equals OD by the same principle, because OB, OD both are the radius of the circle. And we have defined AB equal to CD, right? So I think you can see three criteria which shows that triangle AOB is exactly alike to triangle COD, or we can say triangle AOB is congruent to triangle COD by side principle, or SSS principle, right? So from this, by CPCT we can get AOB equals COD, right? Corresponding parts we can get as they are overlapping onto each other, so we can easily say these two angles must also be equal, right? The corresponding parts of congruent triangles. So we have proved that equal chords subtend equal angles at the center. And if you find out the converse of it, if the angles subtended by the chords of a circle at the center are equal, then the chords are also equal. Or this is the other way around. If two chords which we don't know whether they are equal or not, if two chords subtend equal angles at the center, then the two chords must be equal. And this can also be shown through different characteristics or different congruency rules using mainly the side angle side criteria, right? So let us move on. The next topic, perpendicular from the center to a chord. So you can see we have drawn a perpendicular to the chord AB. So OC we have drawn as a perpendicular to the chord AB, right? So this statement is given as a theorem also. The perpendicular from the center of a circle to a chord bisects the chord. Or if we draw a perpendicular to a chord, it bisects the chord. Or we can say in the given figure AC is equal to BC, right? Whenever a perpendicular is drawn to a chord, it bisects the chord. Now let us see how. So let us do simple constructions. We join OA and OB, okay, to make the solution simple. So let us consider AOC, this triangle, and BOC, this triangle. Let us consider these two triangles. Now we can see angle ACO, this angle is equal to angle BCO, right? Because both of them are 90 degrees, right? Both of them are 90 degrees. So these two angles are equal. OA is equal to OB because the lengths are the same as that of the radius of the circle. And OC equals OC, which is common to both of them, right? So here we have three conditions again to show that these two triangles are exactly alike. So we can easily say triangle AOC is congruent to triangle BOC by RHS rule. Now how RHS? We have a right angle, which we have shown here, right angle, hypotenuse, which is this one, and a side, right, which is this one. So we have got a right angle, the hypotenuse and the side. So we can say that these two triangles are congruent to each other by the RHS rule. So by CPCT we can say AC equals BC, right? As these two are exactly alike, so their corresponding parts must also be equal, right? So AC equals BC, and thus we have found out that the perpendicular from the center of the circle to a chord bisects the chord, right? So we can use this theorem to solve many questions very easily. And the converse also states that if the line drawn through the center of a circle to bisect a chord is perpendicular to the chord, right? The line drawn through the center of a chord to bisect the chord comes out to be perpendicular to the chord, right? In the theorem above we have given that we know that the line drawn from the center to the chord is perpendicular, but in the converse we know that the line from the center actually bisects the chord, and from there we can easily get that both these lines, the chord and the line from the center, are perpendicular to each other, right? So we can also use this to solve different questions. So let us look at circles passing through 3 points, or we have to find out how many circles pass through 3 given points. So let us start off with 1 point. circles passing through one point, and if you try to find out, you will see that there are infinitely many circles passing through one point, right? You can see we can have one point for all these circles common, and you can even draw bigger and bigger circles having that single point in common, right? Two circles can intersect also at one point, right, if they only touch each other, either externally or internally. So circles passing through 2 points, if you try, you will again find out that there are infinitely many circles as well. Like if you draw one circle and consider 2 points and try to draw circles through these 2 points only, you can draw bigger and bigger circles passing through only these 2 points. And this is shown in one direction, and if you go on doing this in other direction, you will end up with the figure something like this. You can see the central circle, we have taken 2 points as common, and through these 2 points we have tried to draw as many circles as possible, and you will find out that there are infinitely many circles which passes through 2 given points. Now let us consider 3 points. Now if we consider 3 points which are non-collinear, right, it should be non-collinear or they should not lie on the same line, then through these 3 points you will find out that there is only one circle passing through them, right? If 3 points are given which are non-collinear, then there will be only one single circle passing through these 3 points. And we will now find out how to draw this circle, or how to find the center of the circle and the radius, so that we can draw the circle very easily. So let us try it out. But here we can take this concept as a theorem. There is one and only one circle passing through 3 given non-collinear points, right? This statement can be also taken as a theorem. So now how do we find the circle and its center if 3 points or 3 non-collinear points are given? So here we have A, B, C, the non-collinear points. As you can see, they are not lying on the same line. So let us see how to find out the center of the circle and the radius, so that we can easily draw a circle with the compass. So first step is joining all the points, or we join AB and AC, right? You can also join BC as well, it doesn't matter, any 2 points will do. So we have joined AB and AC. Our next step is to draw the perpendicular bisectors of the line segments we have got. Orange one is the perpendicular bisector of AC, violet one is the perpendicular bisector of AB, right? Now the intersection point can be taken as the center, and the distance from the center to any of the points given, either from this intersection point to A or to C or to B, these any of these can be taken as the radius, and you can draw a circle very easily. So what were the steps? Let us recap. First 3 given points were there. We joined these 2 points, right? We joined any 2 points with the third point. Then we drew the perpendicular bisectors, and wherever they joined, we drew a circle taking the radius as the distance from the center to any of the points given. Either we take OA as the radius, or OC as the radius, or OB as the radius. Any one we can take as the radius. Now why do we do like this? You can see if we are drawing the perpendicular bisectors of a line segments, right? If we are drawing a perpendicular of a line segment, perpendicular bisector of a line segment, now we have learned that the line joining the center and the chord, the line from the center to the chord, if it is perpendicular to the chord, then it bisects the chord, right? And if we can find the intersection point of such two perpendicular bisectors, it will be the center, right? If this was the center, then if we had drawn a perpendicular line to AC and it bisected it, then it must have been the center. Now if we had drawn a perpendicular bisector of AB also from the center, then it would have bisected AB also, right? So here must be the center, and thus we can easily draw a circle using this simple concept. So let us solve one question based on this. If two circles intersect at 2 points as given, this is one point of intersection, this is one more point of intersection, prove that their centers lie on the perpendicular bisector of the common chord. Now this question is a long one, but it is a very easy one if you follow step by step. So our first step for solving any question in geometry is to draw the figures according to the given question. So let us find out what is not given in the figure. We need to know which is the common chord, right? And we need to know which is the line joining the centers, right? And obviously the line joining the centers will be this line, right? So let us see how we can draw the figures. So here is the common chord. You can see if we draw a chord which is passing through the two intersection points, the chord is common to both the circles, right? The chord is common to both the circles. You can see the chord is common to this circle also and this circle also, right? Here is the chord for both of them, and here is the line joining the centers. Now we have to prove that this chord is perpendicularly bisected by this line, or we have to prove that this angle is 90 degree, right? We have to prove that this angle is 90 degree or this angle is 90 degree, or the angle which is created by the intersection of these two lines is 90 degrees and the common chord is bisected. We have to prove these two things, right? We have to prove these two things. Now let us see how to do this. So we do a simple construction. We join the centers with the common points. We join the centers with the common points of intersection, right? And we name them for easily writing them down. We name the center of one circle O and the other O prime. Then the common points, we name them as A and B, right? So let us consider two triangles, OA O prime and OB O prime, right? We are considering this triangle and this triangle, right? So let us see how we can find out that these two triangles are alike. If we can find these two triangles are alike, then we can move a step ahead to find out how we can show that the angle at the intersection point is 90 degree. So let us start with the first step. So in these two triangles, we know OA equals OB as the lengths are equal to the radius of the smaller circle, right? OA is equal to OB because OA and OB are both radius of the smaller circle. And once more, O prime A is equal to O prime B, right? Because these two are the radius of the bigger circle, right? So two criteria we have got, and the third criteria, you can see O and O prime, this line is common to both of them, right? This O prime line segment is common to both of them. So we have got three sides which are three corresponding sides which are equal to each other. So we can easily say triangle OAO prime is congruent to triangle OBO prime, right, by the side criteria or SSS criteria. Okay. So from this, by CPCT, we get angle AOO prime. Angle AOO prime, which is this angle, is equal to angle BOO prime, which is this angle. These two angles are equal because they can overlap onto each other by keeping OO prime as the fixed line segment, right? They can just overlap onto each other. So their corresponding angles must also be equal. AOO prime and BOO prime, these two angles are equal by CPCT rule. Now let us construct or let us consider the two smaller triangles on one side. Let us neglect this triangle now, these two triangles which have been caused by the earlier case. You can see in the earlier case we had considered the bigger triangles OAO prime. Now we want to consider these two smaller triangles so that we can include AB within the triangle, right? Now to include AB within the triangle, we have considered two smaller triangles with sides OA, AC and OC, or triangle AOC, and we have considered one more triangle which is OBC, right? Triangle OAC, this one, and triangle OBC, which is this one. We are considering these two triangles, right? Now here we can see once again OA equals OB, right, because it is the radius of the smaller circle, and angle AOC is equal to angle BOC, right? These two are equal as we had got from this proof, right? We had got from this that these two angles are equal. Now we have shortened the arm to the intersection point, which is C, and are calling this angle AOC and BOC. So these two angles are equal, and OC is common for both of them, right? OC is common for both of them. So once again we have got three criteria to prove that these two triangles are exactly alike. So triangle OAC is congruent to triangle OBC. OAC is congruent to OBC, right, by the side angle side criteria, SAS criteria. Now from this we can easily say CA equals CB, right, because as these two triangles are exactly alike, their corresponding parts must also be equal. So CA is equal to CB, or C is the midpoint of AB, right? If C is the midpoint of AB, we have proved one of the criteria, which is OO prime, or the line joining the centers, is actually bisecting the common chord, right? So OO prime is the bisector of the common chord. Now we need to prove one more criteria, that is both the lines are perpendicular to each other. So let us see how we can prove this. Angle OCA equals OCB. Angle OCA, which is this angle, is equal to angle OCB, which is this angle, right? So these two angles are also equal, right? This angle and this angle, these two angles are also equal because they can exactly overlap onto each other, right? So corresponding parts are equal, or corresponding angles are also equal. So OCA equals OCB, but both these angles are linear pairs, right, because they are lying on a straight line, which is ACB, right? These two angles are equal and they are linear pairs. So angle OCA plus OCB is 180 degrees, right? Because they are lying on the same straight line. Now if we replace OCA with OCB and find out by simple algebraic calculations, you will end up with angle OCA equals OCB, which is 90 degree, right? If two angles are on a straight line and both of them are equal, obviously both of them has to be 90 degrees, right? 90 degrees plus 90 degrees gives us 180 degrees. So both of them must be 90 degrees. Angle OCA equals OCB equals 90 degrees, or we have proved that these lines are actually perpendicular to each other, right? We have found that two angles which are there, angle OCA and angle OCB, these two angles are 90 degrees, right? And of course their vertically opposite angles, which are BCO prime and ACO prime, these vertically opposite angles must also be 90 degrees. Or we have proved that OO prime is actually the perpendicular bisector of the common chord, right? So what we have done here, first we had considered the bigger triangle OAO prime and OBO prime, so that we can find out one of the criteria to be used in the second conditions in the second set of triangles, right? From the first set of triangles, the bigger triangles, we have found out that the angles, individual angles, these two angles are equal, right? And we have used these in the next proof, which was showing that these two triangles are exactly alike, and from there we have found out AC equals CB, or C we have proved as a C we have proved as the midpoint, or OCO prime, or the line joining the centers, is actually bisecting the chord. And to find out the angles, we again use the CPCT of what we have got, and we have proved that the angles of these two triangles, the base angles, are actually linear pairs and also equal to each other. So of course both of them must be 90 degrees, right? So the angles of intersection is 90 degrees, and also where they intersect, they bisect the chord AB. Therefore the line joining the centers is actually bisecting our common chord, right? So this is how we have we have proved that OO prime is the perpendicular bisector of the common chord. So you see how we can easily use the earlier learnt topics or the theorems to solve these questions, right? So here we have learnt about circles. We have just reviewed what we had learnt in our earlier classes, and then we learnt about the angles subtended by a chord at a point, right? Then the perpendicular from the center to a chord, which actually bisects the chord, and finally we have learnt about circles which are passing through three given points. Thank you, and see you again.